Hello. So in yesterday's video, in video 121 in my pure math series of videos, you can watch that if you've not already seen that. We discussed that if 3 to the power of x is equal to 100, then that means that log base 3 of 100 is x. So remember that these logarithms that we looked at yesterday, logarithms tell you the power that you need to raise a certain number by in order to obtain another number. So a logarithm in base 3 of 100 tells you the power, so tells you the x value you need to raise 3 by in order to get 100. So that's what we discussed yesterday, how we can use these logs. So let's go into a bit more detail today. So in other words, if a to the power of x equal to b, where a and b are just some real numbers, I'll just say that a is a bigger number than 1 for the purposes of this video today. I mean, it could be bigger than 0. As long as it's bigger than 0, then it's fine. Actually, let me just change this to 0 because it could be bigger than 0 too. I mean, it can't be negative numbers just because if you've got a negative base there, as we discussed yesterday, when you take fractional indices of negative bases, you get undefined maths errors in your calculator. So we just want to make sure that these bases are always positive. So you've got a positive number in there to the power of x equals b, then that means that the logarithm in the base of a, so that base number of a, so logarithm in base a of this b is going to be equal to x. So that's what that means generally for a general a and b, and where b is just some real constant. So let's look at this again in a little bit more detail then. So what we can think of is we can think of this log base a of x to be the inverse operation of a to the power of x. So why can we think of that? Well, if we look at the equation that we started with before, so this a to the power of x equals b, if we do this log operation of a base a on both sides of the equation, so log base a of a to the power of x is equal to log of base a of b, then as we get before, because what we notice from back here is that the way that we define logs is we say again that a log is the power that you need to raise the base by to obtain the answer there. So log base a of b we know is x. So we know that this is x here, so this is going to be x. So what this gave us here, this result here gave us, is that it gave us x. So we applied a log operation to an exponential operation, this a to the power of x, which is an exponential operation. So we can think of this log base a as the inverse of a to the power of x. And why can we think of that? Because remember from our work on inverse functions, if f and f minus 1 are inverse functions, then it means that when you apply the inverse to f of x, you get x. So when we apply this log function onto this exponential function, we get x. So you can think about these operations, these exponential operations and these logarithmic operations as inverses. So now let's think about whether this is actually a function. So is log base a of x actually a function? So let's say that a is bigger than 1. So remember, if a is between, I'll do this in a different color. So remember that if a was between 0 and 1, you had an exponentially decaying graph like this. We're just going to focus on the exponentially growing graph in today's video. We're only going to worry about these exponentially growing graphs, just because normally we deal with logs with a base bigger than 1 generally is what we deal with logs. We don't really need to worry about logs with fractional bases. So yeah, so if we've got this logarithm with a base of a bigger than 1, then we know that the exponential graph is going to look like this, going through 1 there. So we know that these logs are inverse operations of the exponential functions. So we can kind of use our mirror line there, the y equals x line. So remember again from our work on inverse functions in my inverse function video. So remember that these functions are reflections over the line y equals x, these inverse functions. So what that means is that we can reflect this graph over to get a graph like this, something like that, where you've got like an x-intercept there of 1. So that's an x-intercept of 1. So this would be the graph y equals log base a. So log base a of x. Sorry, let me write that again. Log base a of x there. So the question is this a function? Well, to me, yes, it is a function. It does look like a function just by looking at the graph here. So we've got basically a one-to-one function. So for every input, you get one output, every input, one output, every input, one output, every input, one output. So it's a one-to-one function, and every one-to-one function has an inverse. So yes, it is a function. Sorry, every one-to-one function. Yeah, I mean, every one-to-one function is a function. So yes, it is certainly a function. Yeah, we can say that this log base a of x is a function, and it's the inverse function of this a to the power of x function there. So let's go to the next page then. So yeah, I'm just writing out these facts again. That if f of x equals a to the power of x, so for example, if f of x equals 3 to the power of x, then the inverse function is going to be log base a of x. So the inverse function in this example there would be log base 3 of x. So that's just really the key point to take away from today. But let's look at these graphs of y equals log base a of x, where a is greater than 1. So let's look at these graphs. So what I've drawn here is a graph of y equals log base 2 of x. So what happens if I draw a graph of y equals log base 3 of x? So, I mean, it's still going to go through. I mean, let's actually draw our exponential graphs, our inverse functions, our exponential inverse functions, to kind of get a picture of what our log graphs would look like. So this graph here, we're going to call this log. So this is 2 to the power of x there. That's y equals 2 to the power of x. Oh, sorry, 2 to the power of x. Going through one there. So y equals 3 to the power of x is going to be a steeper graph, isn't it? So it's going to be a little bit steeper. Still going to go through 1, but a little bit steeper like that. So that's y equals 3 to the power of x. So log base 3 is the inverse of that. So log base 3 is again going to go through 1 there. It's going to be a little bit, looking at this reflection here, it's going to be a little bit more shallow there. And it's going to still be quite shallow. I mean, my graph's not a very good graph, but it's going to be like this. It's going to be quite shallow, a little bit more shallow than this one. Yeah, so the y equals log base 3 graph is more shallow than the y equals log base 2 graph. So if we keep on increasing the bases, I mean, let's go to a base of 5 now. So let's say y equals, so this blue line here, y equals 5 to the power of x. So with this one, again, this is not a very good sketch. Again, we're going to reflect it over this y equals x line. I'll just draw a few more dashes there. So again, this is going to be even more shallow, this log base. And let me just emphasize, this is supposed to be a 5 there. This is a 5. So 5 to the power of x. So the log base 5 graph is going to look something more like this. So again, more shallow, something like that. I'll try again. Yeah, something like that. So that's gonna be your log. I mean, again, I mean, it shouldn't be going down here. Let me try and be a bit more accurate. It's always, so these graphs are always increasing, because the reason why these log graphs are always increasing is because the exponential inverse is always increasing. So if they're always increasing, then the logs are always increasing, because it's reflected over the y equals x line. So a graph of y equals log base 5, for example, would look like this. So y equals log base 5. So the idea of these graphs, these log graphs, is that if you keep on increasing your base, you get a more shallow gradient, you get a less steep gradient. So your graph is actually more shallow compared with logs with a smaller base. But the opposite happens with the exponential graphs. When your base is bigger, you get a steeper graph, because you're raising a bigger number to a power. You're taking powers of a bigger number, so therefore it's going to be a bigger exponential growth. But when you're taking logarithms of a bigger base, you're actually getting a smaller growth, because your powers are getting smaller, because essentially the power that you need to raise your base by becomes smaller, because your base number is bigger. So that's why your graph here, your graphs are actually getting essentially your y value is getting smaller for bigger bases in your base there. So yeah, that was just a summary of summarizing this fact here, that yes, so logarithms are inverse functions of exponential functions. Obviously, because we can see here that the logarithm is a one-to-one mapping, so it's a function, and it is a reflection over the y equals a to the power of x line. We can also say the same as well with these fractional bases. So again, let's just say that a is between 0 and 1, for example. So in that case, remember that our exponential graph is going to be an exponential decay. So it's going to be something like this. So let's just say that that's y equals a half to the power of x there. So reflecting this over the line over this mirror line, y equals x there, that mirror line there, to get our inverse function. So it's going to be something like this. So this point is going to go to over there at 1. So it's going to get a coordinate of 1. What we can see is that the graph is asymptotically approaching this 0 there. So it's going to do something like this. It's going to basically go in this direction here. It's going to cross through there and asymptotically approach like that. So yeah, this like I'll do it in blue instead. Let me just sketch this in blue. Yeah, so that would be our log graph for a fractional base. So log of base a half x. It's log of base a half x. So yeah, with this graph here, it's just going. It's basically the negative of so it's the reflection over the x-axis of these graphs here. So with this log of base a half, it's actually the reflection of this log base 2 graph. So remember, this log base 2 graph was something like this. So this is our log base 2 graph. So y equals log base 2. So actually what happens is that these logs in these fractional bases are actually the inverses. So a fact to realize is that log base a of x is actually the negative of log base 1 over a of x. That's kind of an interesting fact. I mean, we'll come on to, when we do the laws of logarithms in a couple of future videos, probably sometime this week, we'll come on to some of these facts in a bit more detail. But one fact you can realize is that if you've got a log in base, for example, base 3, then that means that the negative of that will be the same as log base of 1 over 3. So this kind of fact that I've just written there, because we can see that they are reflections over this x-axis, this y equals 0 line there. So yeah, that was again a summary of how you can sketch these logarithmic graphs, and the fact that these logarithmic graphs are actually the inverse functions of their corresponding exponential graphs.